Hello, and welcome to the fourth of these videos, where today I'm going to be talking about acceleration. To first talk about acceleration, I think it's important that I first mathematically define a topic I covered in the last video, that being velocity, in this case, average velocity, the average being denoted by a line above our variable symbol. Average velocity is equal to delta x over delta t, where x represents position, t represents time, and delta represents a change in your variable. This means you should read this as average velocity equals your change in position divided by your change in time, or the rate of change of position over your time interval. This should make sense, as if you have an object whose position changes very largely in a small period of time, that object will have a higher average velocity than if you have an object whose position changes very little in a much larger span of time. Consider a car versus something more slow, like a snail. But what about acceleration? Well, acceleration has an identical relationship from velocity to position as acceleration to velocity. To see this, consider the following formula and compare it to the one we've already written. Here we see that average acceleration is equal to the change in velocity divided by the change in time, or the rate of change of velocity. This is an identical relationship between acceleration and velocity, as velocity has a relationship to position. This means that if you have an object whose velocity is changing over a time interval, then that object must be accelerating. To see this more concretely, I think it's important to consider two examples. The first of these examples will be a toy car. Let's say a toy car is accelerating from rest to 1 meter per second in the span of a second. This means that the car is going from 0 meters per second, so 0 meters per second, to 1 meter per second over the time interval of 1 second. Bringing back our formula for average acceleration, we see that average acceleration is equal to the change in velocity over change in time. While we have not specified direction in this case, we can still interpret this as a velocity, as we assume that the directions are both the same. So, writing this formula down, we see that the change in velocity is equal to 1 meter per second minus 0 meters per second divided by 1 second minus our starting time, which is 0 seconds, and this is going to be equal to 1 meter per second squared. This squared seconds in the denominator is often a key indicator that you are dealing with an acceleration. However, there's a far more nuanced version of acceleration that occurs when your velocity vector is not changing in magnitude, but changing in direction. To see this, consider the slightly more advanced example of a ball rotating on a string in a circular path where the velocity of the ball is not changing. How should you interpret this? Well, if you imagine attaching a tennis ball to a string and swinging it in a circle around your head at a constant speed, you are not increasing the speed of the ball, but you are changing the direction of the velocity vector. So at position A, let's say the ball has this velocity vector, but after it has traced out a circular arc, gotten to this point in the circle, it now has this velocity vector at point B. My question for you is, has this ball been accelerated in any way? The answer is yes, because if you remember, velocity is a vector quantity, meaning that it has both a direction and a magnitude. In the example of the toy car, we saw how changes in magnitude of your velocity vector cause acceleration to be present, but in this example, we see that changes in direction also imply a present acceleration. Here, if you compare vectors, velocity vectors A, just pull that down from there, and B, we see that they are not equal. Why? Because they point in slightly different directions. So even though the magnitudes of both these vectors are the same, because they point in different directions, there has been some acceleration that has acted on this ball. This is a slightly more difficult topic, but just remember that acceleration depends not only on the change in magnitude of a vector, of a velocity vector, but also the change in direction of a velocity vector. If you have any questions concerning acceleration, please feel free to let me know. Otherwise, I hope you have a nice day.